Rules of inference. They are very often used in proofs in mathematics and computer science, and they are simple to understand. Let us start with a definition with an argument. An argument, by an argument we mean a sequence of statements, which we call premises or hypotheses. We may also call it hypotheses, معطيات, and that end with conclusions. This hypothesis gives conclusion. So it is a very natural thing, but we are describing it in word. An argument is some statements, hypotheses, معطيات, premises together that gives a conclusion. So we have two parts: premises, conclusion. Premises, conclusion. Okay. An argument is said to be valid if, so I have to write here, if the truth of the premises implies the conclusion is true. If the premises are true, then the conclusion is true. If that happened, then the argument is said to be valid. And we will learn this in details in a while. So in this section, in this lecture, we will do the following. First, study rules of inferences for propositional logic, and then we go to introduce rules of inferences that contains quantified statements for every, and they exist. Remember, these are called quantified statements. And then show how the rules of inference for propositions and for quantified statements can be combined. So first, for propositions, rules of inference for propositions. Second, rules of inference for quantified statements. 3, combine these two together. Okay, this is our plan for today's lesson. Okay, so a valid argument in the propositional logic. So let's see a very simple example. Consider the following argument, the following example. It says, we have a statement says, if you have a current password, then you can log into the network. So if you have a password, then you can log into the network. The second statement, you have a password. So we have two things. If you have a password, you log into the network. And the second thing, the second statement, you have a password. These are the premises. These are the hypotheses, al-mu'tayat. The conclusion then, therefore, you can log into the network. So here we go. Let's use P for you have a current password. Q for a statement, you can log into the network. So we will have this argument. This is called argument. So we have P, if P, then Q. We have it in hand. So we started here with rules of inference. We have two statements. P gives Q. And you have P. So you have Q. So again, you have the following statement to be true. P gives Q. And you have P already. Therefore, you will have Q. This is what we are saying here. Therefore, this means therefore. So if we have one, P gives Q, and we have P, then we have Q. This is the very first rule of inference. It is that easy. It is that intuitive. So in here it says, when both P gives Q, when this is true, and we have P in hand, both of them is true, then we know that Q must happen. Okay? So P is happening. And we know that if P is happening, then Q is happening. Then Q is happening. And that means also the statement, see, here we go again. We have P gives Q. in hand, and we have a P there. So altogether this will give Q. So this is a tautology. This is a tautology. Let me clean that again. So in here you have the following. You have this statement number 1, and this is the important thing. So statement number 1 and the statement number 2 will gives me the conclusion Q. So this is a tautology. Whenever this is a tautology, then 1 and Q, then 3 dots, therefore 1 and 2, then 3 dots, therefore Q is happening. So rules of inference in here, this one, with the Q, all of this is equivalent for having this to be a tautology. Okay. Now, we say this form of argument is valid. Now we're saying form of argument is valid because whenever all the premises are true, then the conclusion is true. So we are saying that again. Remark, the argument form, okay, these are the premises. We have something, some statement plus other statement and other statement, and we have and all the time. So we have to have all the premises, all of them. And this is called the conclusion. The conclusion. So this is a statement, an argument form. We call it an argument form. And the hypotheses are called the premises here. And this is the conclusion. Is valid whenever this statement, this form is a tautology. Okay. So things will become more clear if we keep going. Okay. Rules of inference for propositional logic. Okay. Therefore, now how to show an argument form is valid? We said we must go and prove it is a tautology. But doing so using truth table might be very tedious. For example, if we have 10 propositional variables, then we will have 2 to power 10 of rows in the truth table. So that will be a very long way to go. Instead of going or using truth table, we will first establish validity of some relatively simple argument forms called rules of inference. So this is what we want to reach. We want to develop rules of inference that are very basic, very easy. And these ones will help us to prove that some arguments are valid. Things will become more clear. So again, these rules of inference can be used to build as building blocks to construct, this is what I'm saying, to construct more complicated valid argument. So we have simple rules of inference that will help us to work with more complicated argument forms. Okay. So let us see these rules of inference. They are easy to understand, very intuitive, but we need to put them in some rules, in some forms. Look at this. The first one, we have just worked an example for it. It says if we have P in hand, so P is happening, and if we have the following also happening, which says if P is happening, then Q will happen. And we have P happening, so we will conclude that Q will happen. So it is that easy. So if we have P, and if we have P gives Q as true statement, then for sure we will have a conclusion that Q happened. So again, this is P here, P and So this is the P, and P gives Q, and the conclusion is Q. And this is called modius ponens. We will not worry about the names. Okay. Let me now explain the second one. This says if not Q is happening, and we have the following to be true. P gives Q. Then not P is happening. And this needs to be explained. Let me take this here. This one. P gives Q. Let me take it here. P gives Q. The contrapositive of this is, and you should know that, you should always remember what that means. The contrapositive is equivalent for that statement. So we can replace this statement by saying not Q gives not P. This is the contrapositive. And you should know what that means. Good. So we will replace P in here. We will replace this P gives Q with this statement. And now we already have not P, so I will say here, right, not Q, sorry, not Q. So I have these two statements. Now look at them. This says not Q. We have not Q in hand. And this says if not Q, then not P. So if we have not Q, then we will conclude not P. But we already have not Q in hand, then we will have not P. So this is the conclusion, and it is here. So that makes us understand the second rules of inference, which is called modus tollens. Don't worry about the name. So the hypothesis is not Q. P gives Q, and we have and here, and the conclusion is not P. Okay. Now the rules of inference, the remaining ones are easier. You can conclude it right away. Now this says P gives Q. If we have P, then Q happen. And this says Q gives R. If we have Q, then R happen. Now look at it. If we have P, then Q happens. If we have Q, then R happens. So if we have P, then R happens. So it is the conclusion. Again, this is first premises. This is the second premises, and we have and then this is the conclusion, and this is tautology. So this is the column of tautologies. All of the columns, the second columns, are the tautologies of the argument forms. And it is called hypothetical syllogism. Don't worry about the names. Okay, now let's see the one next. This says, let me use green for this. This says we have a statement which is true. P or Q. That means I either have P happening or Q happening. One of them at least has to be there. If not P is happening, then Q is happening. If not Q is happening, then not P, Q is happening, then P must happen. So one of them must be there. One of them. So this says P or Q. And this says P is not happening. So Q must happen. This is the conclusion. Again, P or Q means if one of them is not happening, then the other is happening. Okay? Now, the second premise here says not P, so P is not happening. So we have to have Q happening. Now, here we have P or Q and not Q, and the conclusion is for Q is happening, and this is the name. Okay, let's see this one. Let's use blue for it. If we have P happening, the conclusion P or Q. So if we have P already in hand, can we say P or Q? Yes, because we have P in hand. P is happening, so this is easy. P gives P or Q. Okay. These rules of inference are very easy. Now, this one says P and Q. If we have both happening, P is happening and Q is happening. So for sure P is happening. This looks like very easy. This is the conclusion. Very intuitive or very funny. And this is called simplification. So two more rules of inference to go. If we have P happening, Q happening, the conclusion P and Q is happening. Okay, here it is. This is a conjunction, we know it. Here, this I like this resolution. So pay attention to this. This says first thing P or Q. P or Q. Either P happening or Q happening. So if not P, which means P is not happening, then we must have Q, because one of them at least must be there. Okay. Now this says not P or Q. Either not P or Q. So if not P is happening, I'm sorry, if not P is not happening, so not P is false, which means P is happening, then R must be happening. Okay? Now again, so we have two cases. P or Q and, so let me go here. This is P or Q and not P or Q. So look at it here. Look at it here. Now, if P is happening, that means not Q is not happening. So R must happen. Good? This is, now we concluded if P is happening, then R must be happening. Okay? Let us assume now P is not happening. So we go here in this one, here. P is not happening, but we have either P or Q. And since P is not happening, then Q must be happening. So good. So we have the following. If P is happening, then we must have R. If P is not happening, then we must have Q. So we must have either R happening or Q happening, and this is the conclusion. This is called the resolution. Okay? So these are all the rules of inferences. Let's see an example. State which rule of inference is used in the argument. Okay. If it rains today, then we will not have barbecue today. So here P, it's raining today. So that means if it is raining today, then, this is for then, we will not have barbecue. So if we go for Q, we will have barbecue. That means we will have not Q. We will not have barbecue. Okay. Now, if we do not have barbecue today, which means not Q, then we will have barbecue tomorrow. And we will have barbecue tomorrow is R, so not Q gives R. Okay, so actually we will have a Q. I can keep it that way, but if I want to keep it that way, or I will add not to Q, so Q will become we will have barbecue today. But let me leave it as I got it here. Let Q means we will have barbecue today. So we will have P or gives not Q, and we got not Q gives R, so P gives not Q, and not Q gives R, but we have P in hand, so that will mean P gives R. So this is the rules of inference here, which is called, what was it called? Let's go where it is. The hypothetical syllogism. Okay. Okay, using rules of inferences to build argument. Okay. So let's have some fun with this example. Let me take it. Okay. Show the premises. Okay. The question says if we have all these premises, then show that they lead to this conclusion. Okay? So let's do it. This says it is not sunny this afternoon, then it is colder than, it is not sunny this afternoon and it is colder than yesterday. So we will say it is sunny this afternoon. We will say this is P. So here we will have P and it is colder than yesterday. So it is colder than yesterday. We will give it Q. So we will have P. This is not P, it is not sunny. And Q. So this is the first in here. So let me go here and say this is now not sunny and it is colder than yesterday. So we have not P and Q for this. Okay. Now let's go to the second one. We will go swimming only if it is sunny. So we will go swimming, we will call it R. So this is R. It happens only if when it is sunny. Sunny is P. So if we go swimming, then it is sunny. So R gives P. So for this we have R gives P. Okay. And now let's see here. If we do not swim, if we do not go to swimming, that means not R. Then we will take a canoe trip. Let's go for we will take a canoe. We will take a canoe trip to be S. So here we will have R giving not R if it is not sunny. If we don't go to swim, then we go take a canoe trip. Okay. And what else we have? If we take a canoe trip, we said this is S, then we will be home by sunset. And this is the conclusion. This is the conclusion T. This is the conclusion here. We will call it T. Here is the conclusion. So if we take a canoe trip, which is S, then we will be home at sunset, and this is T. Okay, now we have these promises. Now if we get them together here, they are here now. So we have these premises. And we want to have all that together to give the conclusion. Okay, good. So all these we will join them by an and, and then we will prove all these together will lead us to T. And to do that, we will use rules of inferences. Now here, let's see what's happening. Now we start with a premise. Now what I gonna use star, that means something we already have, and we will use So these are the premises. These are the ones here. Okay? Good. Now, we start not P and Q. It gives not P. This is use the simplification. This is the simplification. I am putting it here. So we have P and Q. We have a statement and another statement. So we will have one of them. We will have each of them is happening. So we will take the first one, say. So we have not P and Q. So not P is happening for sure. Now, what we do here, we will combine these two together. We will combine the not P we already concluded from the rule of inference and a premise that we already have in hand. It says not P, this is we have, also we have R gives Q. So if we use now this here, this says if we have P, a statement P, and that statement implies Q, then we will have a Q. Okay? Okay, so we will use 2 and 3 again, model tolerance, where it is. Okay, we are not using this, sorry. We are using modulus tolerant, which says, shall I write it again? We have not P, and we have P gives Q. This is the modus tolerance, the ones we have seen already, and we will use it now. Okay, to jump from here to here, we will use this. Okay, so we have P gives a Q and not Q, then we will have P in hand. So we have not P and R gives P, not. Okay, good. So what happens here, P takes the rule of Q. This is Q, but sorry. This has supposed to be Q here. This is not Q, not Q. Now to apply this, which is written in red, to move from 2 and 3 and then conclude 4, we will substitute for Q in red, we will replace it by P. And P in red will be replaced by R. Then we will have not R happening. So sorry, this will this conclusion I did not complete it. This will say is not P happening, will be happening. So this is R goes for P. Okay, good. Now we have 4 already concluded, and we have 5 in hand. So we will use 4 and 5 to conclude 6, and to use that we will use modus ponens, the one in here. Now it says not R gives S. This is 5. This is a premise. معطيات already have. Not R gives S. But we have not R already in hand. So therefore we will have S. Okay? Now again here we concluded 6 and we have 7 in hand. We have S and 7 says premise S gives T, therefore we conclude T. Wow. And then we have reached T this way. And what we have done so far, these are premises, the ones we concluded, and then we join them with and then we get T. This is to clarify what we meant when we wrote an argument in its general form. Let me go back so that now you know what that means. go back more. So we have premises joined together with an AND here. This is what I wanted to show you. Premises joined together with and all of them will give the conclusion. Okay, let us continue. So actually, let me see, I think I have another example of this form, and I'm thinking to leave it to you, or yes, please, I will leave this to you to do it the same way. Let me write only that we will these. Okay, P gives a Q. What is P? P means if you send me an email, this is for P. Then I will finish writing a program. This is a Q. So here we have P gives a Q. So I will write the premises and will leave the steps for you to conclude. Okay. Now, if you do not send me an email message, and this is not P. Okay, good. Then I will go to sleep early. So let's use sleep early means R. This statement is R. I will go to sleep early is R. So we have here not P gives R. Now, if I go to sleep early, this is R. Then I will wake up feeling refreshed, and this is S. So here we have R gives S. Okay? All these conclusions, all these premises, we want to show that they will lead to the following conclusion if I do not finish writing the program. Okay? So writing the program is, we denoted, I will finish writing the program was Q, so this means not Q. Then I will wake up feeling refresh, which is S. So the conclusion is not Q gives S. So okay, we want to use these premises here to conclude this conclusion, and this is what we are saying here, these premises to conclude this conclusion. And there are the steps. Again, in blue here are mu'tayat, hypotheses that we already have in hand. P gives Q, using the contrapositive of it, so I'm doing that. Not Q gives not P. Now we have this premise here. 3, we already have it in hand. Now join 2 and 3. Not Q gives not P. And we have in hand not P gives R. So we will conclude not Q gives R. So good. Now we have 4 is the conclusion and 5 is a premise. Not Q gives R and R gives S. So we will have not Q giving S, and then we are done. We have reached it. We use the hypothetical syllogism, whatever. Syllogism. Okay. So this example was quick. I was planning to leave it, but we are done it. Okay, resolution. I already said I like this resolution. I will explain it again. This says we either have, if we have P or Q, and not P or R, then we must have either Q happening or R is happening. Again, let me explain it again. If P is happening, then not P is not happening. And so we must conclude R is happening because we either have not P or R. Okay? If P is happening, then not P is not happening. So we must have R happening. Now, again, if we have P is not happening here, P is not happening, then we must have Q happening. So we concluded If P is happening, then we must have R in hand. If P is not happening, then we must have Q in hand. So we either have Q or R, and this is the conclusion. Okay? Now, show that the premises, all these together, this and that, will make us conclude P or S. P or S. Let us see. Let's replace this in here by using that distribution. So we are distributing this in here and in here. So we got P or R and Q or R. This will make us conclude that we have P or R is happening in hand. Okay? And here we have, let me move it to here, not R or S is happening. So, not, R or P, not R or S. So, if we go back to the resolution here, which variable takes the role of P is R. And actually, let me write here, R and P will take the rules of each other, and also P will take the rule of Q, and S will take the rule of R. I'm saying the rule between here and between here. And this will lead us to conclude. So we have R or P, and so let me rewrite that. So we have we have the following: P or R and S or not R, and for sure this will give us P or S using these substitutions. Okay. Okay, rules of inference for quantified statement. This is part 2, as we have said in the introduction. And they are very intuitive, very easy. Now, if we say, if we have that P of X is happening for every X, so we will conclude it's happening for some C, where C is in the domain, because it is happening for all values in the domain. So it happens for one of them, each one of them. This is called universal instantiation. Instantiation. So we have a property that is happening universally, but for instance, at a specific element, it is happening. That specific element is C. That instant we stopped at is C. So it is happening at C. Now, universal generalization. If P of C is happening for arbitrary C, so we have a domain of all elements, and if we take any element of them from that domain to be C, and we find that P of C is always true, so we will go for a generalization and say P of X is true for all X, and this is the conclusion. Okay? Now, about the existential quantifier. If we say there is some X that P of X is happening, that means P of C is true for some C, and we know that. It means, and now we call it existential instantiation. Okay. If P of X is happening at some C, then there is C where P of X is true. Okay. Now this says if P of C is true for some C, then this is true. There exists X such that P of X is happening. Okay. So if you go to the domain and find an element C where P is true over that C, then we will say there exists X such that P of X is happening. There exists a value for X which is C. Okay, so this conclusion, these rules of inference are very intuitive, but here we put them in symbols. Okay, example, show that the premises here, these premises will give us this conclusion. So we have these premises and we want to conclude this conclusion. A student in this class has not read a book. So a student in this class has not read the book. So if we say C of X represents a student in this class, P of X represents X student has read a book. Okay, here it says everyone in this class passed the first exam. So P of X, let it be X passed the first exam. Then we want to conclude that some who passed the first exam has not read the book. So there is a student who passed the exam, which is P of X true, and he did not read the book. So it is not B of X. Here we go. So there exists some student such that he passed the exam but he did not read the book. So we want to have that conclusion from what? Let's go back here. This means here, this. A student in this class has not read the book. A student. So there is somebody who is a student and he did not read the book. So there exists a student and he did not read the book. So there exists a student, he did not read the book. This statement says that everyone in this class has passed the exam. So everyone in this, so this goes for here. Everyone in this class, so everyone. So if X is a student in the class, then he passed the exam. So for every X, if he is a student in the class, then he passed the exam. So we want to show both of these statements here, this one and this statement will give us this is true. And we will use the rules of inference we have just seen. Okay, now let me go to blue and say these are the ones that we already have. Okay, now we have for every x, C of X and not P of X. So we conclude there is someone for this thing which applies to this thing applies to him. So again, there exists X such that C of X and not P of X. So let that X be A. So we have C of A and not P of A. We have this and that, so we will conclude C of A is happening. Okay, now we will use 3 and 4. We have 4 in hand, that's why I marked it with the blue. It says we have C of A is true, and we have that for every X. If C of X, then P of X. For every X, if C of X is happening, then P of X is happening. Okay? But now we are saying in 3 that C of A is happening. So we will conclude that P of A is happening. And then we concluded this. P of A is happening. Okay? Now again, let's go back to 2. It says C of A and not of P. This is and that. So we will take that, which is add not of P, and then we conclude 7. Good. Now using 6 and 7, P of A is happening and not B of A. So we have that statement P of X and not B of X happening for an element which is A. So we will say there exists an element such that this is happening and we have reached it. Okay, good. The last thing is combining rules of inference for propositions. This is the first part. This was the first part of the lecture. And quantifying the statement. This was the second part of the lecture. Okay, now we have this modus ponens already. If P is in hand, and we know that P gives a Q, then Q is in hand. And that applies for the universal property. It says, if for every x, P of x, having P of x in hand gives a Q of x, and we have this information and this information, and if we have P of A is true for some A, then we must have Q of A is true. Now again, if we know that for every x, if we have P of x happening, then Q of x is happening. This applies for all x's in the domain. Okay? And then here we say, if we know that P of A is happening at some element, then we must conclude that Q of A is happening. Because we have P of x happening gives Q of x happening for any x. So if for A, P of A is happening, then Q of A is happening. So, and this is the conclusion, and we just write it this way. For every x, P of x gives the Q of x, but P of A is happening, so Q of A is happening. And there is an example for it. If we say P of n is the statement n is greater than 4, Q of n square is less than 2 to the power n. And we know that for every n, if we have n greater than 4, then n square is less than 2 to the power n. So this is the statement of that. Now, P of 100 is happening, right? This is true for 100. And therefore, it follows that Q of 100 must be happening. And we have that conclusion. Just look at it. It's so easy. Okay. And sorry, the one above we called it universe. What we called it? We give it a name. Universal modus ponens, because it looks like this. This is why I wrote it here. Universal modus poning. Okay. And then there is another one, which is universal modus tollens, because it comes from here. Remember, this is if we have P giving Q as a true statement, P gives a Q, but Q is not happening, then not P is not happening, or not P is there. Okay, so here we go. For every x, P gives a Q, but for some A, Q is not happening. That means for some A, P will not be happening. Okay, and this brings us to the end of the lecture.